startup?
I'm part of the Australian.
Okay. And how about the other consortium for which you came over here to Delhi last year? How is it? I mean, picking
That's
up?
the same. That's the same one.
Oh, okay. It's the same one. Okay.
Yeah, so we are live on YouTube now, so we can start the event if you're okay. So we'll start now. Uh, yes. Hello everyone. A very good evening and welcome to Indian Institute of Technology, Delhi. Thank you very much for joining this webinar today. My name is Shaumik Siddhanta and I am the webinar facilitator and an assistant professor at the Department of Chemistry, IIT Delhi. And we are very pleased to bring you this content today, which is the first webinar of the Diamond Jubilee lecture series that IIT Delhi is organizing round the year. Our distinguished speaker for this inaugural lecture of the series is Professor M. Stanley Whittingham. This webinar has been arranged by the Department of Chemistry, IIT Delhi, and sponsored by Author Cafe. Before we start, a couple of technical details. If you have any questions, please type them in the Q&A box, and we will try to get at least some of them through to the speaker after the talk. We are also pleased to have Professor Ashok Ganguly, our Deputy Director and Senior Professor with us here today. I request Professor Ganguly to speak a few words to inaugurate our webinar series.
Good evening, everybody, and very hearty welcome to Professor Stan Whittingham. As students of solid-state chemistry, we have known him for a long time for his work in oxides and intercalation, and finally with the breakthrough in lithium battery technology. Professor Whittingham, IIT Delhi is celebrating its Diamond Jubilee year. So we were founded in 1961 on 16th of August. And this year, our year-long celebrations started on 17th of August and was kicked off by the Vice President of India. And we are continuing several programs throughout the year. In the webinar series, this international seminar is the first in that series, and we are so happy that you have found time to help us and talk to our students and many others around the country through this YouTube webinar. And IIT Delhi, as you know, is among the top institutions, not only in India, but globally ranked. Our students have done extremely well. We have very strong alumni all over the world, especially in the United States. And most of them are involved in setting up industries. They are in many startups, etc. So currently, IIT Delhi has around 600 faculty, 11,000 students, and it is growing very fast with 3 campuses. And we are now in the future, also the government wants to go international campuses, but we have international linkages right now. We are very thankful to you to talk to all of us on your Nobel Prize winning work. Many of us, as you know, have grown up in learning solid state and materials chemistry. And we have grown up with the change. What used to be solid state chemistry has moved over to materials chemistry and chemistry of materials these days. And of course, the length and breadth of the subject has increased, bringing soft materials and porous materials and many other kinds of materials. Earlier, we were only dealing with hard materials like oxides, etc. So I will stop here and just ask Somik to take over with the my last line that
Thank you.
Thank you, Professor Ganguly. And I would now request Professor Ramanan from the Department of Chemistry, IIT Delhi, to introduce the speaker. Over to you, Professor Ramanan.
Good evening, everyone. It's really a privilege and honor for me to introduce the speaker for this evening, Professor Mike Stanley Whittingham, Distinguished Professor of Chemistry at Binghamton University, New York, USA. Professor Stan Whittingham was one of the 3 scientists to receive the 2019 Nobel Prize in Chemistry, along with Professors John Goodenough and Akira Yoshino, for the development of lithium-ion batteries that created a rechargeable world. The technology has not only revolutionized portable electronics, but is also currently making a greater impact on electric vehicles and grid storage. It's important to note the 3 men worked independently on different aspects of chemistry, physics, and engineering of cathode and anode materials that eventually led to lithium-ion battery. Think for a moment, in these COVID times, this webinar, or for that matter, the way all our education and the universities could not have functioned but for this discovery of lithium-ion batteries, which is indeed energizing our mobiles, laptops, and computers. Professor Stanley Whittingham was born in Nottingham in UK. His BA plus doctorate degree at Oxford University. After completing his doctorate in 1968, he moved to Stanford University to do a postdoc with Professor Bob Huggins in the material science. I need to mention here one thing. Around that time, Europe was a leader in the area of solid-state research. Like many men who were encouraged abroad to have overall experience, Stan Whittingham also proceeded towards where he carried out interdisciplinary work, and also he got the opportunity to work a variety of materials. After a few years, he was employed to initiate work on alternative energy storage systems for electric vehicles. This is where he laid the foundation for a lithium-ion battery by creating an innovative cathode material based on layered titanium sulfide that could intercalate lithium ions by combining with lithium anode. However, the lithium anode hampered viability of a commercial battery, but later Professor Goodenough, who was at Oxford at that time, extended this concept, and Sony finally came out with the first battery in the early 90s. Now, after spending almost 16 years in the industry, initially at Exxon for a long time and later at Schlumberger, Professor Whittingham moved to State University of New York at Binghamton. Now it is known as Binghamton University. There he established the Institute of Materials Research and later also the Materials Science and Engineering program. Currently, he is the director of Northeast Center for Chemical Storage and also Distinguished Professor of Chemistry at Binghamton University. Over the years, he has received many awards and recognition, and especially after receiving the Nobel, we don't need to go into the full details, but in 2002, he was honored with the Battery Research Award of the Electrochemical Society for his many contributions to intercalation chemistry and battery materials. In 2004, he was elected a fellow of the Electrochemical Society. He was also the founder and principal editor of the journal Solid State Ionics. In fact, when he started, he was very young. That was early 80s. And in addition, he has been in the editorial board of many, other American Chemical Society, Royal Chemical Society journals. Finally, I want to add that 3 of our own students from chemistry department went and worked with him at Binghamton. In fact, one of them has already, started a lithium startup. I think probably that's what a minute ago Professor Whittingham said, that they are already started manufacturing lithium batteries. Currently, one student is doing her PhD with him. Now, on behalf of IIT Delhi and the chemistry department, it's really our pleasure to have Professor Stan Whittingham to deliver the inaugural webinar on the occasion of IIT Delhi celebrating its Diamond Jubilee. Professor Whittingham, now you can kindly share the slides also.
I hope you can all hear me. And Dr. Whittingham, thank you very much. I fondly remember your days at Binghamton. You were my first postdoc, I think, a few years ago, and we did some great research there. What I would like to do today is describe some of the origins of the lithium battery and some future challenges and opportunities. Let me first thank the US Department of Energy, who's been supporting my work for the last 30 years. So they've been very productive and helpful. So I also should thank what was then Esso. They went to Exxon, and now ExxonMobil, who were willing to take the risk to not only get into lithium research, but do development work, engineering work, and actually manufacturing of cells. So I show you a picture of me a few years ago, and also to point out that in those days, we basically used single crystals in the battery, and it looks like today's batteries are going back to single crystals again, lower surface area, less bad reactions. On the right-hand side here, I show you one of the original giveaways that Exxon gave to potential customers. This particular one is still in my office. It's still working. So it shows that very well-made lithium batteries can last a very long time. And at the bottom here, I show you some larger cells. These are about 6 inches by 4 inches by about 1 inch thick, that Exxon showed at an EV show in 1977. So they built large cells, and in the end they got out of the business because it wasn't large enough, but they showed the feasibility of lithium batteries. So these same cells that we built back then, I show you a couple here. Bob Hamlin, who headed up the manufacturing entity, and I searched our basements and managed to find these 2 cells. And these 2 cells, plus a marketing brochure, are now in the Nobel Museum in Stockholm. So you can see them there. And these cells are perfectly safe. It looks like they're going to last forever. So let's just look at what was special about titanium disulfide. Why did we want to look at it? It has a layered structure, as I show here. So these are TiS6 octahedra forming a sheet. Then between these sheets sit the lithium atoms. And these are exactly the same structures as lithium cobalt oxide and all the major materials we use today. The big advantage of titanium disulfide, it has essentially metallic conductivity. So you don't have to mix carbon or other conductive materials with it, which means it can react all over its surface, not just where the carbon, the TiS2 and the electrolyte meet. So we can get very high current densities. I show you here, this is 10 milliamps per square centimeter, higher than any of today's batteries work. No carbon black, and this is the 76 cycle. And the difference between the discharge curve and the charge curve is just the resistance of the electrolyte. So this worked exceptionally well. And I'll list all my colleagues who made this activity possible. TiS2 is still of great interest. Linda Nazar, Waterloo University in Canada, used it as a cathode for magnesium cells, and her magnesium cells now hold the record for the highest capacity for a magnesium cell and also the best recyclability. So you can see this is her discharge and charge curves. This is for, in fact, the spinel version of TiS2, not the layered version, but the layered version is very similar. Cycles very well. You can see the capacity fades a little bit, but not much. Close to 100% Coulombic efficiency. The problem is the very polarizing magnesium ion does not diffuse very fast. So this data is at 60 degrees centigrade compared with lithium that's at 21. And you can see the voltage of the lithium cells about 2 volts. In this one, it's about 1.3 volts. So magnesium cells are much lower potential, which means the energy density is much lower. The other challenge with magnesium cells is that no one has been able to get more than 1 electron transfer. And the whole purpose of magnesium was hopefully to get 2 electrons, but that has not been successful. Another use of these layered sulfides has come up recently, and this is as a support for sulfur and lithium sulfur cells. And I show you 2 examples. I won't go into any detail, but this on the left-hand side, this is using a liquid electrolyte, and you can see they're getting about 800 milliamp hours per gram. And this is quite stable. These are just 3 different ratios of vanadium disulfide to sulfur. So you can see again, the capacity is good and the cyclability is good. And on the right-hand side, I show you again some data of Linda Nazar's. This is now in an all solid state cell. And you can see again, she's got 50 cycles out of this with good Coulombic efficiency and good capacity. So these metallic materials are both useful as active materials and as supports. And in this particular application for sulfur, the vanadium disulfide is also electrochemically active. So let's just do a little bit of history on the lithium battery. I'll show you a few of the key issues with it. So a lithium battery has an anode, where the lithium is stored on fully charged, a cathode, where the lithium goes, and in between is an electrolyte, and this has to be organic, or it could be a ceramic, because otherwise it would react with the lithium metal. And in between this interface, a protective layer is formed when the battery is first built, which protects the organic from the lithium metal. So in 1972, we used lithium metal. Exxon eventually switched to lithium aluminum because of the possibility of dendrites and fires. And then Akira Yoshino was working at a carbon company, switched to a carbon-based anode. And this again is what I show you here. This is graphite structure. So you can store the lithium within the graphite. The issue here is the graphite takes up half the volume of the cell, and you need 72 grams of graphite to store 7 grams of carbon. So it's not all that efficient from an energy density point of view. So present researchers are now working on tin or silicon substitutes where we can store up to 4 lithiums per silicon or tin. And again, the holy grail is really to go back to lithium metal if we can make it safe. On the cathode side, we started with lithium titanium disulfide. John Goodenough, who was at Oxford, was working on the magnetic properties of lithium cobalt oxide, and he recognized it had the same structure as titanium disulfide and decided to test it out, and it worked very well. So that technology, he worked with the Atomic Energy Authority in Britain, and then they licensed it to Sony. Cobalt is very expensive, so the trend has been since there to substitute the cobalt by nickel and manganese and some aluminum. So almost all the batteries built today are NMC type batteries, except in your cell phone and your laptops where pure lithium cobalt oxide is still used because it has the best density in there. You can pack more kilowatt hours inside. John then came up with lithium ion phosphate, and that was very popular for maybe 10 or 15 years. It faded in interest recently because of its lower energy density, but it's used in some utility grids, and of late, Tesla plans to use it in all their Chinese vehicles. The issue with lithium iron phosphate is you're carrying along that heavy phosphate group, which reduces energy density. So we would like, if we're going to carry a phosphate group, to actually put 2 electrons in there. So we've been looking at various phosphates where we can go from 2 oxidation states to 3, and I'll describe some work on Bandio phosphates where you can go from 5+ to 3+. So let me just show you a few examples of where lithium ion batteries are used. Whilst we're in Stockholm, 2 of the physicists, Nobel laureates and myself, had a live discussion with astronauts on the International Space Station. On the left is a lady from United States whose parents were Swedish. On the right is an Italian astronaut. At the time we had this discussion, they were in the middle of installing lithium-ion batteries to store the energy from the solar cells on the space station. And they commented that lithium-ion batteries stored twice as much energy in the same space and lasted twice as long. So they were very happy about that. Let me show you a few other examples of where lithium-ion batteries are used. Obviously, you all know they're used in your cell phones. And at this time, probably everybody in the audience has at least 1 lithium-ion battery on themselves, if not 2 or more. They're being very actively used for storing solar energy and wind energy. And this is a 16 or 32 megawatt hour storage facility on a wind farm in West Virginia in the US. On the right, I show you a number of electric vehicles. This is in fact my wife and I. We rented an electric vehicle in Bermuda a year ago for our 50th anniversary. And the renters told us, do not drive all the way to the far end of the island and back without recharging. It won't make it. There's a charging station at the other end of the island. So we drove to the other end of the island, went to recharge it, and the recharging station was still being built. It wasn't available. So fortunately, we found one on the way back, and we managed to just about get the car back to the hotel before it ran out of energy. On the right-hand side over here, I show you 2 trucks. These are on the test track just north of Seattle in Washington State. This is what we call a 16-wheeler. And I think you can see the large batteries there just behind the cab. And I took this on a drive around their 1-mile test track, drives very smoothly. And next to that is an electric vehicle garbage truck. And this is an excellent use of electric vehicles because it stops, start all day long, lifting garbage cans up and down. So this is excellent use. In the bottom here are 2 electric vehicles the UK ambassador took to Stockholm for the Nobel ceremony. This is a Jaguar, and on the right is a London taxi built jointly between the British and Volvo in Sweden, and she used this one to go to all the ceremonies. So Britain is very heavily involved in going to electric vehicles. So a lot of people ask me, well, you got the Nobel Prize, so no need for more research on lithium batteries. I say it's just the opposite. If you look at what we get out of lithium batteries today, it's less than 30% of what we theoretically should be able to get out. So if we look at volumetric capacities here, we're getting between 11% and 25%. On the gravimetric, it's about 25%. So we believe we should be able to double that. And in fact, I'm part of a large consortium in the United States called Battery 500, whose goal is to get these actual practical values to 500 watt-hours per kilogram. The major challenge is the carbon anode. As I mentioned earlier, it takes up half the volume of the cell. We have to replace it. We've also got to get a higher lithium content in the cathode. So this is a layered oxide. In fact, we only use about 60% of the lithium. I'll get into that a little bit later. But from a solid state chemistry point of view, what we need are higher ionic and electronic conductivities. We can then use thicker electrodes. If we can use thicker electrodes, we can get rid of half the current collectors and half the separators. So that's really where most of the research is going. Let me mention the anode briefly. As I said, we started with lithium. Exxon and Moly Energy, where Jeff Dahn was, also used lithium. This tends to form dendrites. And these are some dendrites that Russ Kernelli, who was at Exxon, showed using in situ measurements just with an optical microscope. So some of these cells were used by AT&T. They were built by Avastor in Canada, and these were in fact all solid state cells. Lithium anode, a polyethylene oxide, electrolyte, and I think a vanadium oxide cathode. And a number of these caught fire within just a few months of installation. And that was the end of lithium metal in most batteries until the present day when there's a few applications coming up. So we had a research project to, in fact, replace graphite. We chose tin to do that with. It can double the capacity. If you see at the bottom here, this is carbon. This is gravimetric, volumetric, and we put carbon at 1. So you can see if we use tin, we can double the volumetric capacity. With just 2 lithiums, we gain a bit more by going to 4 lithiums, and it increases the gravimetric capacity a little bit as well. In 2005, Sony had commercialized a tin-based anode. We found out that was in fact a 1-to-1 alloy with cobalt. Obviously, cobalt's too expensive, so we set out to replace it by iron. And I show you some of the data here. You cannot use tin itself because it expands 300%, which means it eventually decrepitates into fine powder, and its surface is too reactive. So the surface keeps reacting with the electrolyte. So by making this alloy, we're protecting the surface, and it's also encapsulated in some graphitic carbon. So you can see the results on the right here. This is the volumetric capacity. Okay, in ampere hours per cc. This is graphite. You can see why graphite is used. Absolutely stable, loses no capacity at all. And here is our tin iron compound. It's more than double the capacity of graphite. And this is at the C rate, which means we're doing the charging in 1 hour and the discharging in 1 hour. So very high rate material, very good material. So we've shown the feasibility of using alloys, but clearly tin is a bit expensive and it's a little heavy in the long term. So let's switch over to the cathode. Almost all today's batteries use these layered oxides, so this is exactly the same structure as TiS2. So metal oxide, octahedral joined together, lithium in between. In the real materials, there's some exchange because we have entropy involved. So there's 3 to 5% of lithium will be in this layer, and 3 to 5% of nickel will go into the lithium layer. A little bit is good because this stops the layer shifting relative to one another when you take the lithium out. The big challenge with these materials is the best material for energy density, which is high nickel, is unstable. So let's look at this now famous plot out of South Korea. If we look at the equimolar material, that's 1/3 nickel, 1/3 cobalt, 1/3 manganese. It has the lowest capacity, 160 milliamp hours per gram, but is stable to over 300 degrees centigrade. If we go to the highest nickel material, which is about 85% nickel, you see it now has about 208 milliamp hours per gram, so much higher, but its thermal stability is only 220. So it's 100 degrees less thermally stable. And what this means is the less thermally stable it is, the more reactive its surface is, so the more likely it is to react with the electrolyte. And you see plotted on the right-hand side is capacity retention. And the higher the nickel, the worse this is. So we have to solve this. And one of the ways of doing it is to put a little aluminum in there, which stops all lithium come out. It helps stabilize it. And you can use magnesium to a certain extent, but it doesn't solve the whole problem. Nickel and cobalt are still expensive. Ideally, you'd like to switch to all manganese as its lowest cost, but there are many challenges with manganese because it has a distortion in the lattice and doesn't cycle very well. So for our Battery 500 consortium, we use the 60% nickel material. It shows excellent cycling, has very good materials properties, characterization is good, electrochemistry is good. And you can see here the capacity of this material is about 350 watt-hours per kilogram. And this gives us very stable behavior. You see the cell capacity in ampere hours on this side. And this particular cell is now, I think, about 400 cycles. And there's no fudging the data here. This data was collected by an ex-student of mine, Jay Xiao, who's now at Pacific Northwest National Lab. She was working with Idaho National Lab. And these are the typical pouch cells we use. So after the cycling, we weigh the pouch cell, measure it, so we can calculate these energy densities accurately. So we include everything in this energy density, the pouch, all the inert material. So our target this year was 50 cycles at 400 watt-hours per kilogram. We've achieved that. So we hope to get to about 450 in a year's time. So you can get to higher energy densities, but these are using pure lithium metal. So there's some potential safety issues if you go to a very large size. So as I said, we use 60% nickel. If we want to go to higher energy densities, we've got to use more nickel. So we investigated going to 80% nickel. Don't worry about all the details in here. Basically, this is the lowest current we use. That's the lowest chemical reaction rate. Towards the right, we now have a much higher current. And you can see as we increase the current, the capacity drops down here. Also, we need, for high energy density, very high loading. So we show here from 3 milligrams per square centimeter in the cathode to 23. There's quite a difference in here. And to show this is kinetic, we go back to the original conditions and it's back to normal. You now see in the 811, there's much less of a fall off. So the 811 can tolerate a higher current density. It also can tolerate higher rates, and the amount of loading has less impact. So our program has switched over now to 811 from 622, but there's a few other ways we can, in fact, improve the cycling behavior of this material. So if we look at these materials, this is again 811, here's the structure. This is what the actual powder looks like. in commercial cells and the cells we investigated. The particles are about 200 nanometers inside the primary particles. If you actually use those in the battery, they would not pack very well. Be like using talcum powder or carbon black. So what they do is form these meatballs where these nanoparticles are packed into particles which are 5 to 10 microns across. So these pack in a dense manner, and commercial batteries tend to have these of two sizes, a large one and the small ones that then pack between the large ones. If we actually look at the cycling of these materials, on the very first cycle, we charge them. Here's the charging cycle. This is up to about 4.4 volts. And then discharge follows very nicely. But then we have what's called this first cycle loss. And this is between 10 and 15% of the capacity. And you never get this back again. So we're losing this 30 milliampere hour right from the beginning. So if we want to get a higher energy density, we need to recover this. And this is particularly important because this is at the lowest voltages, so it's at the most stable part of the electrolyte. So we've been studying this and we looked at a number of parameters. What caused this loss? Now, was it the material itself, the electrolyte, or how we made the electrodes? So we looked at a number of parameters and we found a number not important, so I won't go into any detail on these. So the amount of material had no effect at all. The nickel content, again, from 40% to 80%, had no effect at all. The type of carbon we used had no effect, and the amount of carbon we used had no effect. So it's something inherent to the layered structure itself. What did have an effect was calendaring. Let me explain what this is. When you make a lithium battery, you coat the active material onto an aluminum sheet as a paste, you dry it, then you put it between rollers and press it, and this is what the coloring process is. So you can see the black curve here is no calendaring. If we calendar it, you can see it's got a little bit better. But the other thing we can do, on a normal battery, you charge and discharge at a constant current. If after you do your constant current discharge, you then do a constant voltage discharge, as we show here. So this is green one, come down to the cutoff voltage, then we hold it at that voltage, we can recover quite a lot more of the capacity. If we calendar and do the constant voltage discharge, we get even more back. So we know some parameters that affect it, and it turns out it's the last 10% of the lithium. So that's from lithium occupancy from 90 to 100%, that's important. And my colleagues that's in San Diego discovered this by only charging it to say 50%, 40%, 30% of its capacity. It was still lost the same 10%. So it's this last 10%. So this is telling us we got very slow kinetics when we have high lithium content. So we went in and measured the diffusion coefficient. So the black circles here is lithium in diffusion. So we're putting lithium in. And you can see once we get to about 80% lithium, the diffusion coefficient falls off by about 3 orders of magnitude. So this is what's causing the problems. Taking the lithium out, which is the open circles, it's not so much a problem except at the very end a little bit here. So this material is amenable to fast charging. The reason for this, according to Anton van der Ven, is we have a dye vacancy diffusion mechanism. So if this lithium atom here wants to jump to this site, it needs an empty site next to it because it's going to jump from an octahedral site to a tetrahedral site, then to this octahedral one. As you fill more of these lithium sites, so there are fewer and fewer of these dye vacancies, and this causes this diffusion to fall off. Okay. But on the right-hand side, I'll show you another important parameter. If diffusion is rate limiting, then if we raise the temperature, this should help solve the problem. So I show you here 4 curves charged to different voltages, 4.2, 4.4, 4.6, and 4.8. And you can see we get better capacity the higher we charge, so the more lithium we take out. But you'll also see that we're now getting separation of the charge and discharge curves. This is because of surface reactions damaging the surface of the material. If we now do this at 45 degrees instead of at room temperature, you can now see we've eliminated well over 50% of this first cycle loss. And this is at 4.2, at 4.4, at 4.6. It's not quite as good, and you see this separation. So now we're getting more and more reaction of the solid with the electrolyte, and it's much worse at 4.6 volts. So we can't go to these higher voltages at these higher temperatures. But clearly this is again an indication of diffusion limited. There's one slight puzzle in all of this. Lithium cobalt oxide does not show this behavior. Same structure. So we're looking at that. We believe if lithium cobalt oxide doesn't have this problem, then we should be able to modify the structure of the NMCs by either lattice substitution or coating. That should help. So one of my postdocs is now looking at coating this material, and what she's using is a lithium niobium oxide. So we take the commercial meatballs like this one, soak them in a solution of lithium niobium oxide, and then fire that solution at about 400 degrees centigrade. And then you get this brown coating as I show here, and it diffuses a little bit into the particle, just a few nanometers. And you can see the effect of this. So the black one here is the uncoated, unsubstituted, and the others, whether it's 1%, 2%, or 3%, makes no difference. We are recovering some of this first cycle loss. So this coating substitution is helping, and we're looking at a number of newer materials right now which are even better. So this is one solution to this problem, and we hope in the end to eliminate most of this. We won't get rid of it all because we know there's some initial surface reactions. So what is the situation with cobalt oxide? Let me show you again, 811. The black curve here is the curve at room temperature, and this is charged to about 120 milliampere hours per gram. If you now do this at 45 degrees centigrade, it's the red, and you can see it's much better. And if we hold it at 2.8 volts, we get almost all of it back. So that's similar to what I showed you before. Lithium cobalt oxide doesn't matter, room temperature, 45, there's essentially no first cycle capacity loss. So we know we should be able to eliminate this even in the NMCs. We just got to find out how to do it. So let me move on to a couple of other materials which are of interest. I've discussed the lithium cobalt oxide. Lithium Ion Phosphate, I mentioned, is a low-cost, stable cathode used extensively in China. And it's extremely high rate when we make it single phase. We do this by doping it with a bit of vanadium or magnesium, but it has a much lower energy density than NMC. My colleagues here, Sherju Preti and others, are looking at the manganese equivalent that has almost 4 volts. The other issue or good point about this lithium ion phosphate is a tunnel structure. You'd expect it, therefore, to have a higher first cycle loss. It doesn't. It essentially has no first cycle loss. So we don't have that issue here. But the problem, as I say, it has a low energy density. So we're interested in making a version of this that could react with 2 electrons, and we chose vanadium phosphate as that, and I'll show you a couple of slides in a minute. As I mentioned earlier, the ideal would be to have a high manganese content material, and people are looking at that now. And Argonne National Lab looked at a long time at lithium-rich, manganese-rich materials, which had more than 50% manganese, but they had low stability. Others are looking at disordered rock salt versions of this material, but they have a very high voltage change, not a nice plateau like over here. So let's look at this Bandio phosphate. This material, this epsilon phase, was first formed by Alan Jacobson. It has a nice three-dimensional structure, so it should be structurally stable. The phosphate group makes it thermally stable as well. So the goal here is, can we make it an electrochemically active form? And my student Kerry Sue, who's now at Argonne, made this material by reacting vanadium chloride with phosphorus pentoxide in an ethanol water solution. You cannot use pure ethanol because it reduces the vanadium too much. And I should at this point acknowledge Dr. Ramanan, who really introduced us to the hydrothermal approach to make materials at lower temperatures so we can make metastable materials. So this material, we reacted for 3 days. I think 1 day is enough, but 3 days is a nice weekend. If you do that, then you make the hydrogen analog of this material. A low temperature heat treatment gets rid of the protons, or you can chemically remove these protons or electrochemically at room temperature. So make this nice structure. And what we form are these nice cuboids, about 100 nanometer in size, all uniform. And using these materials, we then get this electrochemical behavior. You can see vanadium 5 to vanadium 4 at just under 4 volts, then vanadium 4 to vanadium 3 at between about 2¼ volts to just under 2 volts. And you'll see these bumps here. This is lithium ordering in the structure. And this has no effect on electrochemical behavior, except to make this, when you're actually moving lithium ions, this becomes single phase, so it's very high rate. Now, the key point to note here is the black curve is the first cycle. The purple curve is the 50th cycle. There's no difference. So we have now proof of concept. We can stuff or intercalate 2 lithium ions into a crystalline lattice without hurting that lattice in any manner. So we've got proof of principle here. We've now got a few other challenges to make this material work, but I think others will also work on this material. And I should say this was our Nexus consortium that worked on this. We had theorists working on it, characterization experts, and obviously our synthetic folks. So let me just show you a few conclusions on what's next. We believe lithium intercalation systems will dominate for the next 5 to 10 years. These layered oxides will be dominant, but they will go close to zero cobalt. The phosphates will have key markets, and I expect they're going to grow again now that Tesla's announced they're going to use it in all their Chinese cars and maybe even in some of the lower cost US ones. The key research need is safe and stable electrolytes. These haven't really changed since 1990. And the big challenge now and interest of researchers is, can we use a solid state electrolyte? This will make it much safer, allow us to use lithium metal and maybe higher charging voltages. But I want to leave the message with you that energy storage can help to mitigate climate change, make us greener vehicles, enable renewable energy, and help us eliminate the dirty peaker power plants. These tend to be old coal power plants. We had one of these in Binghamton. They put a lithium battery next to it. Within a month, the coal power plant was turned off and never came back again. And if we do this, we'll leave a greener world for our children and grandchildren. And I would just like to point out that in 2019, India installed the second most solar facilities in the world after China, more than the US, more than Germany, more than any other country. So I will stop there and try to unshare.
Okay, thank you, Professor Whittingham, for the wonderful and stimulating lecture and taking us through the exciting journey of lithium-ion batteries. So we are really living in a world where we cannot imagine a life without lithium-ion batteries, and we are really privileged to hear directly from the scientist, the professor, who is one of the inventors. We have a little more than 500 participants or viewers who have been watching this lecture. And we will now have a short question and answer session. Although we have received quite a lot of questions, but unfortunately, we won't be able to take all of them. So we have sorted out a few of them for Professor Whittingham to answer them. Professor Whittingham, should we start with the questions?
Yes.
Okay. So the first question is from Abra Shao, who asks the question. So here is the question. So lithium has very limited resources, currently 0.0017 weight% in the Earth's crust, while sodium and potassium are abundantly available. So which is like more than 2% weight%. So why not sodium potassium ion battery to make rechargeable battery at low cost?
So the answer is twofold there. One, people are looking at sodium, and if you look back in the 1970s, we, Bell Labs and others also looked at sodium. The issue with sodium, it's larger, so it tends not to diffuse as well. It also melts around 100 degrees centigrade. So people are worried about its possibility in thermal runaway of melting. And if you've got an organic solvent, you can have an explosion. But I think the major issue is lithium has much higher energy density. So the voltage of a lithium cell is between 0.5 volt and 1 volt higher than sodium. So I think you're never going to see sodium in your laptops, your cell phones, and I expect not in your cars because it doesn't have a high enough energy density. I think it's quite feasible it will be used in grid storage eventually. But right now, lithium ion is by far the lowest cost battery material. So it's going to be used. Potassium has about the same cell voltage as lithium. But potassium, because it's larger, is going to have some diffusion problems. And also, therefore, the potassium ions interact with each other more because they're larger. And there's more repulsion, so the voltage changes. The big problem with potassium, it melts at 60 degrees centigrade. So it's very likely to melt in your cell, and then you've got real problems. So I think we should study potassium to understand lithium and sodium better, but I don't see anybody ever building safe potassium batteries.
Okay, thank you, Professor Whittingham. So the next question is like, what is your opinion on zinc air batteries as competitor in automobile sector?
In the automobile sector, no possibility whatsoever. So because the energy density is too low. I think the issue in the automobiles now, and I expect it's also a big issue. I gather India and Delhi are switching over to batteries for their three-wheelers. Is it anything but lithium takes up too much volume, too much space, and lithium ion is probably lower cost than any other system. So no, lithium ion battery is going to be there. I don't see anything bumping them from it at the moment.
Okay. So on a related, one more related question. So what are your views on use of lead-free perovskites for anode materials in lithium-ion batteries for long-term applications considering higher capacity for intercalation? So this is asked by Kartiki.
So this is for lithium batteries using lead-free anode materials, or?
Yes, lead-free perovskites for anode materials.
Okay. I think in batteries, you don't want to use perovskites or anything else if you can avoid it, because that's higher weight, more volume. So you want to go to a metallic anode. I said ideally lithium metal, or if you're doing sodium metal, and if necessary, alloy it with another metal. So I think a number of solid-state batteries are using a lithium indium alloy. It's not quite so reactive with the electrolyte, and it makes better contact. So there's interest there, but I think people are only on very specialized applications. There's some interest in using lithium titanium oxide as an anode material combined with, say, lithium ion phosphate to replace lead acid batteries as a starter battery in vehicles, not for the main propulsion. So there's some interest there.
Okay. So here is a question which has been asked by many young researchers out here. So the question is, what advice would you like to give to all young people, especially for those who have just embarked on a career as a researcher?
Same advice I give to all younger folks. Do something that you enjoy doing. Be happy doing it. Don't do something for the money, because eventually you will be unhappy. And take risks, enjoy yourself. And that's the key thing, particularly when you're young, enjoy yourself. And I think I would say, and I think Dr. Ramanan would say, see the world, whilst you're young. And hopefully once this COVID virus has gone away, we'll be able to meet in person again. But hopefully we won't do quite as much traveling as we have been doing. But for the young folks, enjoy yourself. Have a good time.
Okay, I think that was really enlightening and very inspiring, Professor Whittingham. So I think we are going to conclude the question and answer session here because of the interest of time. So I would like to thank all the organizers and especially all the faculties of the Department of Chemistry and IIT Delhi for organizing this webinar, and especially the director, the deputy director, and the dean of R&D for their constant support and encouragement, and also Professor Ram Ramaswamy, who was supposed to be here, but okay.
He's there. I think he's there. Ram is there.
Yeah.
Okay.
Yeah. I very much here, Somik.
Yeah. So I would request Professor Ramaswamy to say a few words and conclude this session. Yeah.
Okay. Well, Professor Whittingham, this has been a most fabulous way to start our Diamond Jubilee celebrations at the IIT Delhi. And the chemistry department is particularly pleased to have had you kick off the series of seminars for this year. Thank you very much for inspiring all of us, particularly the young folk, and giving us such insight into such important matters, which I'm sure will have a lot of bearing on the world that we will see in the post-COVID era. Just the impact of your work has been phenomenal, and if it helps us to make a more energy efficient, less world, I think we would have really done something. And thank you for giving us such insights into this, into your work, and sharing so much of your work with us. I'd like to also take this opportunity to thank all the colleagues at the IIT, the director, the deputy director, and all the colleagues in the chemistry department for such wonderful support. in starting off this series. Thank you very much.
Thank you. So we officially conclude this session. And thank you for all for joining the webinar today. And we have a small announcement. So the Department of Chemistry will be organizing a webinar almost every week with eminent speakers from all around the globe. So we request you to please visit our webinar website for more information about the upcoming talks. So thank you, and hope to see you again soon. Thank you.
Thank you, Professor Whittingham. Thank you. Bye-bye.
Bye. Hey, Soumik.
Yes, so I think, yeah. Thank you, everyone.
Okay.
Thank you.
That's very well done, man. You organized brilliantly.
Yeah, thank you. Thank you.
Wonderful job.
Thank you. Thank you, President. Thank you.
Hi. Okay, see you, Ram.
Stream. End stream.
Yes.